Okay, thank you for joining us today for the IEEE Tech Talk on SCADA's control systems. Today's presentation is being recorded, so please mute your microphones if you're not speaking and type any questions you have into the chat box. My name is Mike Brisbois. I'm the chair of the IEEE Consultant Network Seattle. And what we do here, we foster and promote the interest of our members. We provide professional and technical services, and we maintain an online membership directory. And arrange and provide technical and management talks like we have here today. The IEEE, as you know, is the world's largest technical professional organization for the advancement of technology. Today's session is co-sponsored by the IEEE Power and Energy Society, and also we have a sponsor, Edward Jones. Some announcements. Join us this Friday for a live in-person Seattle Electrical Conference at the Hilton Garden Inn in Redmond Town Center. So it starts at 8 o'clock. Hope to see you all there. Next Tuesday, we have the live streaming leg of the IEEE Build Tech Conference. Hopefully we can get some really good speakers like Sherry Wen to participate. It starts at 8 o'clock at PST, Pacific Time, Tuesday, live streaming, December 21. Lots of great speakers, so you don't want to miss that. You can sign up today at seattleelectricalconference.com. Today's speaker is Joe Weiss. He's an expert in instrumentation controls, control system cybersecurity. He has published over 80 papers on instrumentation and control systems cybersecurity, chapters on cybersecurity for electric power substation engineering and securing water and wastewater systems. He co-authored the Cyber Security Policy Guidebook and authored Protecting Industrial Control Systems from Electronic Threats. Please welcome Joe Weiss. Joe, take it away.
Thanks. Number one, thank you for reaching out. This is important to me for a number of reasons, but one of them is I happen to be a senior member of IEEE, but I'm also an ISA fellow and the managing director of ISA 99, which I'll talk more about. But one of the things that's been a real problem over the years, and it hit me really hard when years and years ago when I was at EPRI at the Electric Power Research Institute, is IEEE, certainly in the power area, is really the wires area. The generation was ISA. And I could almost never get the two to work together. One of the slides I've got is ISA has a committee on SCADA. And I'm hoping to have Graham Nasby, who's the chair of that committee, speak, but I've got a slide on that. But the real issue is, why in the world aren't ISA and IEEE coordinating more? And it becomes a huge, huge deal when it gets to the world of cybersecurity. So anyways, that's an aside, but I'm glad to be able to do this. A number of years ago, I used to give short courses at the big IEEE PES meetings, including one in Seattle. But it's a lot of things have changed since then. And I'm going to start taking people through the presentation. And I'm really glad to see so many people here kind of on a last minute basis. So let me get this up and running. So the first thing, let's see, can you see my slides?
Not yet.
Okay.
I was like just the header.
All right, hold on. Whoops, I need to get my slides. Just a minute. Hold on. Select the window. Wait a minute. Hold on. All right, here we are. Okay, can you see it now?
No.
Hold on.
I'll steal it away from you and you can take it back.
Yeah.
Sometimes that works.
Okay.
Try it now.
Okay. I'm going to put it up now. Can you see it?
Sometimes there's a delay, but we don't see it.
Let's see. Hold on. Zoom meeting. Share screen. Presentation.
Mike?
Yep, got it.
Okay.
Okay, can you see it now?
Yeah, we can see it.
Okay, I'm going to put
Yeah.
it in.
Can you go? Can you go full screen? Yeah.
Yeah,
There you go.
Perfect.
that's what I just want to make sure I was there. Okay. Ready?
Yep, go.
All right. I normally start my presentations with the title of my book. It's called Protecting Industrial Control Systems for Electronic Threats. The one thing I wished I would have changed is not to use the word industrial, because I have way too many people who go, but I'm not industrial, like buildings or medical or defense or aerospace. We're talking about the same identical systems. So anyways, it's also protecting. Hacking control systems is not difficult. Protecting them is rocket science. And finally, from electronic threats, I left EPRI in 2002, and I went to a company called Kima. And in 2002, we started the first control system cyber security conference. In 2003, when I had my second conference, I had Navy Mission Assurance Dahlgren attending. I had been doing some work for them, of all things, on EMP. And it was supposed to be talking about where should there be a SCADA testbed. This was before Idaho was the SCADA testbed. And this was a totally open, unclassified conference. The first slide they put up was a Navy destroyer was coming into the port of San Diego, and it had its high power pulse radar system on. That Navy destroyer took out San Diego Gas and Electric and the San Diego Water Authority SCADA systems. The second slide on Navy letterhead was the Navy was doing pulse radar testing in the Netherlands and blew up a 36-inch pipeline. Now start thinking about, and this is part of the reason for the presentation and TSA, et cetera, is what we're talking about is causing real physical damage using bits and bytes. And it certainly doesn't have to be malicious. But that's the reason for the term electronic threats, and not hacking where somebody's thinking about a 12-year-old pimply-faced hacker, playing games at a keyboard trying to hack, Microsoft or Windows. You heard before, I've written chapters for electric, water, data centers. These things are ubiquitous. Wherever you are, if you're not in your house, but you're in a building, every building has sensors for monitoring pressure, level, flow, temperature, voltage, current, position, you name it. It doesn't matter where you are. These same things are monitored and the same controllers are used. So the idea of trying to say, well, it's only electric or it's only water or it's only chemicals, this is across the board. These slides, by the way, a lot of these, I gave a presentation to Singapore about a week ago, and it was to law enforcement and cyber forensics. And the why we were here is really important. And especially, are people familiar, or have you heard about this whole log4j thing that's going on? It's entirely the way it's focused IT. And, you've also got all of this stuff on ransomware. Nobody's addressing physical damage and injuries, which is what happens when control systems are compromised. And I mentioned before, all physical infrastructures are monitored and controlled using instrumentation control systems. However, measurements are the input, but instrumentation is ignored, period. Cyber forensics and attribution don't exist for control systems. Control systems are used to control physics, but physics is ignored. All of the cybersecurity training that's being offered is for the quote unquote OT network types, and I'll explain OT in a minute. It's not for the control system engineers. Control system cybersecurity is probably about 5 to 10 years behind IT cybersecurity. But think about Log4j, think about SolarWinds, you name it. IT can't get its act together. How do you expect us being 5 to 10 years behind IT to be able to be, any better? The other thing is the culture is totally broken. You probably heard about the IT-OT convergence. That's wrong. That's just one network talking to another network. What's broken is the culture between engineering and networking. And it is broken everywhere. And we need to fix that. I mentioned, these are ubiquitous. You're looking at, upper left is a nuclear plant. It could be any type of plant. The water treatment, manufacturing, grid. What you're looking on the bottom right is a ventilator, like for COVID. That's a control system, pure and simple. And oh, by the way, the manufacturing for it is a control system. And you got, transportation, obviously. But the point being, control systems monitor and control physical processes in real time, which means they're also controlling physics. The other thing that's kind of interesting, I brought this up when I talked to Singapore, that water treatment facility you see is from the city of San Francisco. About 10 years ago, there was a network administrator in the city of San Francisco who had hijacked the business land for the city of San Francisco. And he basically held it up for hostage. Well, it turns out that the water treatment facility for the city of San Francisco was on the same Ethernet LAN as the business networks. Only nobody knew it. I found out when I was talking to the SCADA manager at the facility. The reason I bring this up was I was sitting next to at a conference the assistant district attorney who prosecuted the person who held everything hostage. He had no idea that the water treatment was connected. And he told me, why didn't you tell me? Well, how do I know I'm supposed to ask? Because he would have known that the water treatment was on that same network, he could have nailed him for a lot more years in prison. Because now you're talking about potential safety of the citizens, in this case of San Francisco. Didn't even know, throughout the trial, and they had thought they had laid out the entire network. But, they don't talk to each other. Now, there's two definitions that are really, really important, and I'll get another one later on. The first one is, what is a cyber incident? To IT, you're connected to the internet, you're running Windows, and data is maliciously being manipulated or stolen. It's all about privacy, and it's all about malicious. The NIST and the Government Accounting Office put out different definitions of what is a cyber incident. Bottom line is, it's electronic communication between systems that affects confidentiality, integrity, or availability. And nowhere is the word malicious ever used. It does not need to be malicious to be a control system cyber incident. And in fact, an unintentional control system cyber incident could easily be, quote unquote, a proof of concept to a bad guy. The other one that's really, really important is the term OT, or operational technology. That was a term generated by Gartner because they didn't know what a control system was. So they basically said, if you're not IT or OT. In most cases, OT are the network people. The relay engineer, the instrument engineer, the turbine engineer, the manufacturing engineer, the safety engineer, or techs do not consider themselves to be OT. They're engineers. Most of them have never even heard the term. But what you'll find is this whole kind of quote unquote IT-OT convergence, which has nothing to do with the engineers. The other point I wanted to make here, a couple of points. There's a term called cyber physical systems. Most of what we deal with are not cyber physical systems. They're physical cyber systems. They're pumps, valves, whatever. Those are physical systems. They happen to have a connection. They are not cyber systems. The last thing I'm going to point out on this slide, what you're looking at is the Purdue reference model. This is not the OSI 7-layer stack. And it's laid out essentially by time. Level 0, level 1 are, if you will, the sensors, actuators, drives, and the process. Level 0 is real time. Level 1 is like milliseconds. Level 2 is seconds to minutes. Level 3 is minutes to hours. 3.5 is really your DMZ. Level 4 is, hours to days or weeks. Level 5 is, days, months, years. And it was laid out not for cybersecurity. This was laid out when they were trying to figure out, the manufacturers, how do you connect a distributed control system to an ERP system? So you could get plant data onto your, ERP or manufacturing execution system, et cetera. That's what this was laid out for. How did we get to where we were? Critical infrastructure, cyber, was actually started in 1998 by Presidential Decision Directive 63. We're what, going into 2022 and we still haven't figured out how to secure anything, or certainly secure what's needed. Prior to 9/11, the engineers owned their equipment, which included cyber. Following 9/11, and I don't have a date and I don't have a document, cyber was made national security. And when that happened, cyber was taken from every engineering organization, and that includes our vendors, and went from the engineers to IT. So not only did you sever the link and the engineers were taken out of the world of cyber, but one other thing happened, and that was to the IT people, and for that matter, OT, cyber is your Ethernet or internet protocol networks and the devices native to the Ethernet or internet protocol network. So that would be firewalls, routers, switches, hubs, cell phones, tablets, all of these things that are native. Well, what happened? All of our engineering systems, process sensors, actuators, drives, analyzers, power supplies, all fell off. To this day, we have no cybersecurity, no cyber logging, and no authentication in anything we measure. To this day. The other thing that happened was, as an engineer, I did lots and lots and lots of equipment forensics. For that, I was looking at high frequency data to look for anomalies. Well, Windows is slow. Windows operates on the order of seconds. So what's happened is all of the data that you would use to understand what's going on with a process has been filtered out. We are actually less secure today than we were 30 years ago, which sounds bizarre. When I gave this presentation, as I was getting ready to do it, the whole point behind this is I was doing lots and lots of work on equipment forensics. Well, vibration monitoring, loose parts monitoring, you name it, is the mechanical analog of intrusion detection. Well, when I brought this up, I was told, wait a minute, you're talking about diagnostics, not forensics. What in the world is the difference? What's happening today is what you're looking at on the left are the network forensics. You're looking at syslog, SIMs, cyber alarm, IP addresses, with plenty of cyber training. On the engineering side, you're looking at system forensics. You're looking at process conditions, the what, not the who. On the other side, it's the who, not the what. The system alarms that we would use for, a relay opening or, high pressure, whatever, is not seen on any cyber monitoring. The corollary is the system alarms aren't seen on any cyber network monitoring. This I mentioned before, I don't know if Graham is on or not, but this is the ISA 112 SCADA standards. And what you'll notice is it says it's pipelines, water and wastewater, power, oil and gas, and other industries. And you can see what's going on. The issue is, how do we get IEEE with such a focus on SCADA to work with ISA in this particular area? And like I say, there is Graham's contact information. And if you're looking, if you simply go to isa.org/ISA112, you'll find this information. But the real issue is, how do we get them? How do we get ISA and IEEE working together? This is the cyber security standards put together by ISA. It's the 62443 series of standards. And they fall into 5 categories. General, which is more, things like terminology and concepts and definitions, policies and processes. The technical, which is like, how do you do risk assessments and what's done via a system integrator rather than a vendor, rather than an end user. And then I'm going to talk more about 4-2, because that's the technical cybersecurity requirements for components, sensors, actuators, drives, you name it. And then there's new things coming on dealing with guidance and application. But part of the plea is also, if people are interested, join. I wanted to point out 2-3. That's patch management for control systems. We did that because patch management for control systems is different than patch management for IT. And patch management for IT has caused multiple cases of shutting down or harming control systems. Now, the standards and regulations aren't adequate when you start talking about control system cybersecurity. For electric, the NERC SIPs exclude all of your field devices. American Water Works Association doesn't even address field devices. IEC TC 57, Working Group 15, is all about networks, nothing to do with the actual equipment. Food, the Food Security Management Act doesn't address control system cybersecurity. Isn't that a scary thought? TSI pipelines, transportation, aviation, none of them address control systems. 62443 is as good as it gets, and it still doesn't address process sensor integrity. The NIST standards, including the latest one, 160 or the latest versions of 882, don't address the 01s, the devices. The NIST cybersecurity framework, part of its core principles is detect. If you can't trust what you measure, you can't detect. TC 65, this is an interesting one. This is functional safety. People talk about control systems not being secure because they're old. This is a communication protocol that is being voted on as we speak. This is brand new. Functional safety and cybersecurity isn't even included. And it's being voted on, like I say, as we speak, by the different national bodies. This is my techie slide, if you will. What you're looking at as you move from right to left, you start with the pure IT. And as you move to the left, that insert that you're looking at with it looks like a control room. Prior to Stuxnet, that's as far as it went. Post Stuxnet, because Stuxnet went after the programmable logic controllers, to try to damage the centrifuges in Iran. We're now starting to look at cybersecurity for the PLCs. Ironically, it was only 6 months ago that they finally put together a group for quote unquote secure PLC coding. But here's where two other things that make this very scary. If you'll notice, you see a cell phone on the bottom. A cell phone today is literally a remote control room. Start thinking what happens if a cell phone is hacked or lost. But the other big thing is you start looking at control valves, sensors, motors, you name it. There is no cybersecurity, there is no authentication, there is no cyber logging. These are, the level 01 devices. You're looking at on the left is variable frequency drives. You're looking at process sensors, chemical analyzers, motor operated valves. When those things have problems, you go boom in the night. There is no cybersecurity. There was recently an ISA conference on factory and site acceptance testing. They didn't address any of this. What they did address were things like, are you using antivirus and is it the latest version? These things can't even use antivirus. A lot of these don't even use Windows. The most popular sensor network, process sensor network in the world is HART. HART is built on 1200 baud modems. That is the most popular sensor network in the world. How are you going to secure when you're built on 1200 baud modems? Let's see, next slide. This is really why we're in the boat that we're in. Cybersecurity is taught in computer science. Computer science in most universities do not require anybody to take an intro course in engineering. Conversely, all of the engineering disciplines, or at least most of them, don't have a requirement to take an introduction to cybersecurity course. You're pushing these two worlds in totally different directions. What you see is what I have is that dot in the middle, control systems security experts. There are very, very, very few worldwide. There are lots of people who are network cybersecurity experts. There are a lot of people who are engineering experts. The biggest issue is how do we train to get the people not to be supermen or superwomen, but to be knowledgeable enough about their area and the other area to know where to go to get to the experts. And a friend of mine brought this up, and I thought it was a great thing. Lack of understanding extends to both IT, OT, and engineering. Just because part of the system is not vulnerable to the threats you're used to seeing does not mean the system is not vulnerable. Well, the network people go, my network is okay, and totally ignore all of the engineering systems. This is from a friend of mine who was doing instrumentation and controls for a major international oil gas company. And here's what he said. I've spent years talking to brick walls and brickheads about the lack of security in field devices. Their response is typically that they are air-gapped and that everything is safe and secure. Irrational fantasy at best. I'm not alone in this quest, but I am definitely in a minority. And where we are living to this day is almost everything coming out of Washington, from TSA, from DOE, from CISA, is all oriented at the networks. The field devices are simply not being addressed. Now, control system incidents are real. There's been over 12 million control system cyber incidents to date. I've been able to find over 1,500 deaths. Well over $90 billion in direct damage. And the point being, you haven't heard of most of these because we don't have control system cyber forensics when you're below the, if you will, the internet network layer. All of that is aimed at the networks. What you're looking at here, upper left, is the Aurora vulnerability. That's when Idaho basically damaged the 27-ton generator. And I'll go into that in more detail, but bottom line, there was no malware involved. What you're looking at next is total and complete destruction of a turbine. As best as we can tell, it was an Aurora attack. This was overseas. What you're looking in the upper right is the DC Metro train crash. And it occurred because of bad data, wrong data, going to the SCADA system, not telling that red line train that there was another red line train that was stopped at the station. And none of that is not being addressed by TSA's rail cyber directive. What you're looking in the middle left is the San Bruno natural gas pipeline rupture. Killed 8, destroyed a neighborhood. PG&E is now a convicted felon because of this. What you're looking in the middle is the Bellingham, Washington, pretty close to where you are. The Olympic pipeline rupture from 1999. Killed 3 people, destroyed a water treatment facility, 3 people went to jail. And the Olympic pipeline, which was a joint venture of Shell and Texaco, went bankrupt because of this. And neither Bellingham nor San Bruno are covered by the TSA pipeline cybersecurity directives. What you're looking at middle far right is the Marucci wastewater hack, where a disgruntled system integrator open the sewage discharge valves. He was caught the 46th time he did it on a traffic stop and dumped, I think it was like 100,000 liters of sewage on the grounds of a Hyatt Regency. Bottom left is tilting. They actually hacked and tilted. They hacked the buoyancy system and tilted an offshore oil rig to shut it down. What you're looking at middle bottom is a 6,400 megawatt hydro station. Turns out it was unintentional cyber. It lifted a 1,000-ton turbine off its pedestal, destroyed this 6,400 megawatt hydro station and killed 75. And by the way, this is in Russia, and Russia initially thought we did it. What you see on the far right is a brand new Navy ship that had to be towed in its final 40 miles into Norfolk because Control System Cyber had damaged the propulsion system. There is essentially no information sharing to this day on cyber incidents. All of the information sharing is on cyber vulnerabilities. And consequently, these real incidents aren't being used in design or training. Just some costs. The first one is an interesting one for here, the one in red. There's been at least one SCADA hack in the US that I'm aware of, where SCADA was totally compromised. In this case, the utility lost SCADA for 2 weeks. There was no equipment damage, but it took 4 man-months to recover. The reason I'm not mentioning the name, and this happens to be in my book, is the utility, because they didn't lose power, did not inform local law enforcement, the FBI, or the electric ISAC. And that's why you don't have a name associated with this. The pipeline rupture that you're looking at, I mentioned before, that's Billingham. The pipeline rupture, you could see the dollars from, that PG&E is hit with billions of dollars. And the refinery explosion and the sensors were very, very much involved in this. This was the second largest refinery in the United States. What people are generally not aware of are the cyber attacks designed to cause damage. And the point being, they're not attacking networks, they're attacking the physics of the systems, which is how you cause damage. You do not cause damage by simply going after a network. So you're talking about Stuxnet, in Iran, Aurora, and I'm going to give you more details on that. Triton was the Russians cyber attacking the petrochemical plant in Saudi Arabia. The attack was not to shut the plant down. The attack was against the safety systems to destroy the plant and kill people. What was interesting about Triton is the first time the plant shut down, it shut down in June because of malware that was in the safety system. They restarted the plant with all of the malware still in that plant. They found it when it shut down again in August. What it's saying is we can't detect a cyber attack that shuts down a major industrial facility. The Chinese transformers, I'm going to talk more about that. And the point being that there have been a number of cases, many, that were cyber attacks designed to cause damage. This is Aurora. This should be unbelievably important to the IEEE people. What Aurora is a class of physical cyber incidents that cannot be addressed by network protection. There is no malware. What this is very simple. And basically almost well, let me put it this way. Every engineering student taking an intro course to electrical engineering is taught, you never reclose or reconnect AC equipment out of phase with a grid. If you do that, you will cause a huge torque and a huge current spike, and it will break it. That's all Aurora is using remote access, in this case, say a laptop, to open and then reclose the breakers out of phase. Mother Nature does the rest. It's like sticking sticks of dynamite underneath that, in this case, that transformer. I mean, that generator rather. And it also does one other thing, and you'll see in the next few slides. This is making the electric grid the attack vector to everything connected to it. So what you're looking at here, and you'll notice on the bottom, DHS declassified all of this information. That's the red line that you're looking at. This is identifying by name, this is scary, by name, the 2 Pacific gas and electric substations you would use to destroy the AC rotating equipment in the Chevron Richmond refinery. This is public. This is identifying every large water pumping station in the state of California and where you would go in the substation to destroy the large AC induction motors. This is all of the large natural gas compressor stations in Pennsylvania and in New Jersey, and where you would use to go destroy them. This is using the electric grid as the attack vector. Now, start going on to what has the Chinese have done. And the reason I'm talking about them is Russia doesn't supply equipment we buy. Iran doesn't. Venezuela doesn't. North Korea doesn't. China supplies equipment we buy. What's happening is, for those that have ever heard, during World War II, the French built a wall called the Maginot Line to try to keep the Germans out. What did the Germans do? They just went around it. Well, what we've done is we've built a Maginot Line for cybersecurity. It's all of the networks. What the Chinese did is put in hardware backdoors in large electric transformers that went around all of the network monitoring. Because of this, President Trump had issued Emergency Executive Order 13920. The point behind this is there is no data to steal where the backdoors were put. The only thing it was there for is to be able to take control of the transformer. The size of the problem, we don't really know. There's over 300 Chinese-made transformers in the US today. We know at least 2 of them have these hardware backdoors. There's a number of these Chinese transformers in the Northwest, the Pacific Northwest. Again, potential scope and impact, unknown. The equipment in the executive order was unique in that everything in it were the control systems and the equipment. What was excluded? The IT, the networking stuff. Why? Because they bypassed it. What you're looking at are things like load tap changers, and we've also had counterfeit transmitters, where you measure pressure, level, flow, temperature. This is safety. These are counterfeit transmitters. What does this mean to safety? And those transmitters can be bought on Amazon, eBay, and elsewhere. Again, we don't know the magnitude of the problem. Here's the other point. About a month ago, DNI, which is the Director of National Intelligence, issued a national intelligence estimate. Normally, this is highly classified. This one was made public. And what you're seeing is DNI, just so you know, it's not, in any way, shape, or form political. 13920 was for President Trump. This is President Biden. DNI assess that transformers, circuit breakers, and inverters are cyber vulnerability risks. I mentioned before the circuit breakers can initiate aurora. Inverters are used throughout our electric grids. Like I say, mention the transformers. And years ago, we were finding logic bombs in digital fault recorders. Again, in this case, not only coming from China, but used in China. Now I want to go on to the whole point of our sensors and our networks. It turns out that all of our network monitoring vendors, all of them assume, famous last words, what assume means. The measurement is uncompromised, authenticated, and correct. This is absolutely wrong. I'm on a joint ISA 84, which is process safety, and ISA 99, which is cybersecurity working group. I mentioned before ISA 62443-4-2, the component spec. What we were doing is using a liquefied natural gas facility as our use case. Blow that up, you take out half of downtown Boston. Well, what we did is took a state-of-the-art wired digital safety pressure transmitter, used everywhere. There's 138 individual cybersecurity requirements in 4-2. This state-of-the-art, you can't get any better pressure transmitter, failed 69 of those requirements. Think about that. The sensors also act as safety interlocks, and you can't bypass them. When you have a problem with a sensor, that flows through everywhere because everything starts and depends on the measurement. Spoof signals can bypass all of your cyber and engineering protections. That is the concern with the Chinese transformers. We need technologies that measure or monitor the sensor values before they become Ethernet packets. Almost everything out there today is looking at the Ethernet packet. It's too late. This is what I was mentioning before. What we need is the raw process signals, not the digital, if you will, filtered signals. What's happening today is modern machine learning is capable of being able to, in a sense, make sense out of the higher frequency noise. This is what we need to do the pattern recognition for sensor and process anomaly detection. I wanted to read one thing too that was in automation. This, I guess it's last month's issue of Automation World. And what it said was that an oft-forgotten consideration in the planning process is the long-term maintenance of any added sensors. Making sure that sensors are calibrated appropriately is a long-term difficulty that few people plan for. Besides experiencing some sensor drift that occurs naturally over time, sensors also eventually fail in industrial settings because they are installed in hostile environments. The point being that I mentioned before, the word correct. How do we know the sensor is actually accurate when we know the sensors drift? This is some work done overseas, in this case in Israel. And it's looking at the raw sensor signals, in this case, in a water facility, looking at the water pumps. What is so important in this figure, the top figure, is where you see the orange is the Windows-based SCADA system doing monitoring. Where you see the blue is offline sensor monitoring. Where you see the white, the Windows-based SCADA, which is the OT network, actually went down. It wasn't hacked, could have been, didn't matter. They lost the OT network. What you're looking at the blue is the offline sensor monitoring kept working. What this means is the sensor monitoring, number one, is ground truth, and number two, can't be affected by IT malware or ransomware. As long as this is offline, you can't get to it, which means this can be one of the only ways to be able to justify continued operation, regardless of what is happening to your networks. And all of these cases where people are shutting down systems due to an abundance of caution, I believe the insurance companies are not going to start to the point of not paying if you're doing that when you didn't have to do that. What we need to do is change the paradigm. One of the things that's happening is there's almost daily, if not weekly, if not daily notifications of cyber vulnerabilities. Just saw one today for Schneider. I mean, you see them for Schneider, Siemens, Rockwell, all of them. You know, it just keeps going. The cybersecurity today is network anomaly detection. Network anomaly detection cannot correlate malware or any form of network anomaly to specific equipment. So you may have a network anomaly problem, but what relay or valve or heat, or anything else does that really apply to? It's really looking from the top down. What we need to do is look from the bottom up, which is what's going on with the process. When you monitor sensors in real time, it's ground truth. It's also agnostic. 90% of the time, a process anomaly is not going to be cyber. It's still important. This is telling us what's going on regardless of why the anomaly. What it's doing is telling you when to take out your tools to start looking. That's what we don't know today. This was the hack that was identified on Friday. This is the Log4j Apache malware hack. I think most people have kind of heard about it. It's supposedly the worst thing that's ever happened. What's ironic is in 2004, not a typo, in 2004, when I had the conference in Idaho Falls, it was in conjunction with the ribbon cutting for the Idaho National Lab SCADA testbed. And what we did was a network, well, not a network, it was a control system cyber attack demonstration. The cyber attacker, quote unquote, at Idaho took a day or two old buffer overflow in Apache Notice Apache. You know, they didn't have the term 0 days at that time, but it was a 0-day buffer overflow. And what he did is he put in exploit or attack code in place of the, you know, what code that should have been there. They sent the exploited code from the Sandia National Laboratories Business Network to the Idaho National Labs Business Network, and from there to the SCADA network. So part of what we were showing is this thing was being sent, you know, 750 miles. But number one, the firewalls didn't block the compromised scripts. In 2004, I don't think they would block them in 2021 either. But here's what it did. It remotely opened a relay. And the relay, you know, you could see it change from red to green, green to red. This is essentially what Aurora was, remotely opening a relay and reclosing it out of phase with a grid. Part of the reason the Aurora demo was done is because even though we did this in 2004, people didn't take it seriously. The second thing was it remotely opened multiple relays with the indication. We called it our little Star Wars thing because you kept seeing the red and green lights going on and off and on and off. This is essentially the 2015 Ukrainian cyber attack. We then remotely opened a relay, but we hid the indication. So you didn't see any status change, even though the relay opened. This is essentially the 2003 Northeast outage. The final thing is we didn't open the relay, but we changed the indication telling you that we did. That's essentially Stuxnet. We did all of that in 2004, and apparently nobody's listening. We now have a project we're hoping to get off the ground. I'm not naming names until we get everything signed, but it's the only one I know of anywhere that's really meant to address the level 01 issue. All of the other things, I just saw a thing today where Siemens and Idaho State and National Cyber, I forget what, anyways, several of the universities are getting together. Only they're not addressing the 01s. Ironically, the only thing that makes it a control system is what they're not addressing. This facility and training that we're preparing is because it doesn't exist. It's to address the 01s, the devices. And one of the things it's going to do or force, it's going to force engineering and networking to work together because neither of them can address what the other is doing. The Holy Grail is connecting process anomaly detection with network anomaly detection. The benefits, we make an intractable network problem a tractable engineering approach. It's forcing engineering and the networking people to work together, but it's identifying deviations regardless of cause. It's creating a real return on investment. Why? Because you're validating or optimizing the actual process conditions. It's reducing the cyber threat space and improving safety. Again, it's not affected by ransomware. This type of thing would have been the only thing to detect, as best as I know, Stuxnet, Triton, and the Chinese attack scenarios, because you're looking at the raw sensor data that can't be compromised. You're basically also authenticating where the signals are coming from. And this improves, like I say, predictive maintenance, process safety, product quality, and cybersecurity. So with that, are there questions? And again, I always tell everybody, sorry for going so long.
No, that's fine. Joe, we have a couple questions in the chat.
Yep, let me look.
Probably easier for you to go through them.
Yeah, So that's what I'm starting. Okay. Let's see, March.
Can you read it first?
Yeah, the first one was just somebody saying that they were here. This is the chat. Are there questions, or would they be in the chat?
Okay, I got them in the chat. Given the confusion language, is your preferred terminology just control systems? If so, isn't it important to differentiate when we are talking about industrial control systems or not?
Okay, the whole point is a pressure sensor is used in a power plant. That same identical pressure sensor is used in a building. That same identical pressure sensor was used, in fact, I think I took the slide out, but in a pharma manufacturing facility. You know, the point being, there is nothing unique about industrial. We came up with that term 15 or 20 years ago. We didn't know how to come up with a better term. When we were doing this in '99, we were primarily, heavy industrial, oil, gas, chemicals, power. And so it didn't seem like it was a problem. It's a problem now. I remember talking to the CISO from one of the largest PC manufacturing or manufacturers in the world. And they told me, gee, they're not worried about it because they don't have any industrial control systems. They had PLCs everywhere. They had sensors everywhere. They just didn't consider themselves to be industrial.
Hey, Joe, we got another one. Do you
Yeah.
offer this access to the database incidents, either commercially or otherwise?
No. And the
Mhm.
reason is I've got a lot of those cases that were provided to me by people who haven't even informed their own management of what's going on.
I see.
So I am an independent consultant. Part of what I've done is given you part of, a course I teach, but without trying to be whatever commercial, if people are interested, I can sanitize, some of the cases, and I've done that any number of times, depending on what they want, and work with you on real sanitized cases.
Okay, we got a comment from Glenn. Control systems versus industrial. IEC has recently approved ANSI ISA
Yeah.
for horizontal application across all control systems.
Yep.
And then he gives an
Glenn, thank you.
example. He gives an example of functional safety protocols, Rockwell chip safe and deterministic protocol guaranteed to operate to the parameters necessary to meet SIL rating. So I guess that's just a comment.
Yeah, the big thing, the reason I brought this up is here is this brand new functional safety protocol. And by the way, you cannot guarantee it because it's not even addressing security. So the answer is it can't meet what it's meant to meet. What Glenn brought up about the horizontal standard is exactly what I was trying to say. ISA 62443, when we first started it, by the way, it was ISA 99 when we started, and the standards were ISA 99. It was converted to 62443 because a number of organizations in Europe and Asia were saying ISA was too US centric. So the 62443s are the security products coming out of ISA 99. And the whole point where I was coming from is when we started 99, this was all the way back in 2002, we consciously said, we're not going to do this as any particular vertical. This isn't water, this isn't chemicals, this isn't power or anything else, because everything was valid, or at least the 80-20 rule, 80% was valid to all. So what finally happened is IEC has now accepted the 62443s as a horizontal standard, meaning it applies to all of these multiple different industries.
Hey, Joe, I had a question. So in the old days, we get PEs, engineering gets PEs. IT, they don't have PEs, and we could lose our licenses. So I think you hit it a nail on the head. Is it seemed like IT folks, they could do any kind of software but not be liable. So I think they changed that, but that's a good point that you brought up.
That, and by the way, what's ironic, I had a friend of mine send me a note the other day. What certifications, what cyber certifications? Well, almost all of this, ISA 99 is starting to offer certifications, people, I'm not talking about equipment, but people certifications that are really oriented toward control systems. The CISSP, CISM, CRIS, almost all of these other SANs, you name it, are really, really oriented toward networks. They are not really oriented toward the control systems per se. And that's one of the biggest problems we've got, is this definition. The fact that you're securing a control system network does not mean you've secured a control system.
Can we open
up
up
that message across?
Joe, can I ask a question?
Sure.
Thank you for such an insightful presentation. You bring out many, many issues which we have not addressed before. I have some questions. You mentioned about these valves, these open and then close. Those are big issues. Is there some way, for example, you also mentioned about back doors. Is there some way we can put those things in the standards? For example, you can use a double checked operation signals to make the valve close, not only rely on one, but rely on several sources. You can double, triple to protect it and to have a positive or negative kind of things, and to prevent extraordinary operations. And that way, if you put that in the standards, may solve many huge issues, because this, we cannot do it with cybersecurity method because they bypassed it.
Right.
So if we build in the designs, it's like a redundant controls into that. And the other things built into standards is to prevent the backdoors. So, and the engineers, they often build the system by the books. And if you want them to consider cybersecurity, it's just impossible for them to know. They don't know what to do. But if you build in the standards, you build in the books, and the system building cannot pass all the inspections and for the customer to receive. What do you think of this way? Because we can have national policies to do that. And I'm the cybersecurity chairs for IEEE USA. And so there are many cybersecurity from many perspectives, from the computer side, from the network side, but for industrial system is have a totally different dimension and which we have to consider. But for engineer to have a better books to follow, probably the best popular is the standard built into the standards, like a cybersecurity standards that have say, if you design this valve, you control, and you have to build in some double or triple validations. Only validated, then you can do that. What do you think of that way?
Okay, what you brought up, in fact, Glenn and I had a discussion on this earlier today, which is what he was saying, signal plausibility. Here's part of our issue.
Yes, okay.
All of our, and by the way, everything you brought up, we've discussed. It's
Okay.
really important.
Okay,
Part of what we're also looking for is to get people to help carry the flag forward.
right,
But it turns out our smart sensors
yes.
have built-in backdoors, built-in.
Building,
Because that's how they're calibrated.
oh,
So part of the issue is
mhm,
we are dealing with equipment that
mhm,
has quote unquote design features.
yes,
And this is what's going to be in for the next 10 to 15 years. Our vendors are
Mhm.
still building these. It's not like, gee, these are the old analog sensors. This
mhm,
is the newest, latest, and greatest.
right,
So we're trying, and even within, I know I'm speaking, and I probably shouldn't say this, but even within 99,
mhm,
we have a large number of people who are network centric, not hardware centric.
right.
That's a real problem. It is a huge problem. Okay.
It is a huge problem, yes.
I've been working some with SAE, Society of Automotive Engineers.
Yes.
Okay.
Mhm,
Seagray isn't doing, one of the things that's happening in August, there's supposed to be a meeting in Paris with Seagray and IEEE, and they
mhm,
stuck, the thing in to be, for ISA to be involved. Okay.
mhm,
There's INCOSI, but
mhm,
also where is ASME? Where is AICHE?
mhm,
All of these, I brought this up before. Where does NSPE fit into all of this too? National Society of Professional Engineers.
mhm.
How do we get, these are things that cross everywhere. If it were simple, we wouldn't have a problem.
Yeah, the situation is because of it's so pervasive, we need to have a centralized policy, centralized method to prevent.
I agree.
And so what is the best way of doing it? We can up to the White House with executive orders as you have to build this way, that way, or some sort, but we have to agree that it is an effective method.
Well, here's our problem.
Mhm,
As best as I can tell, I know I shouldn't use the word all,
mhm,
but I'll use it anyways. All of the people involved today on things coming out of Washington
yes,
are network centric.
I
None of
agree.
it dealing with hardware. None of it.
Yeah, yes,
Period.
yes,
Okay.
I agree.
I've been trying to get CISA to recognize there's a hole there. It's not working.
It's not working. Yeah.
So forth. Okay.
Mhm,
What's happening are people are mouthing the words, and they also mouth the word OT, and people think OT includes this stuff.
mhm.
And so there is this perception that it's being done. It isn't being done.
Yes.
The plausibility piece, that Glenn brought up and kind of what you were also talking about, Sherry, is this is something we were doing 20, 30, 40 years ago. I mean, as a new,
Right. Yeah.
you have to have redundancy and diversity.
Mhm.
And part of it you're asking,
Can we move on?
if the
No.
temperature is going up.
Yeah, sorry, that take you too much time, sorry.
You got a
Anyways.
chance for one more question here.
Yeah,
Okay.
sorry, but we can use your help. I'll leave
Yeah,
it
I
at that.
would like to talk to you more.
Good.
Do we have any last pressing questions for Joe? Dave? Rob? Jonathan? Okay, so we'll table this for next time. So I want to thank you, Joe, for coming in today.
Sherry, first of all, where do you fit in the organization, either IEEE or ACM or whatever. How do we get these organizations together?
Sherry?
You're talking about to me?
Yeah.
Oh, okay. Okay.
We're trying to
Right now,
connect the dots.
right now I'm in it's a IEEE. I'm the chair of the Communication Policy Committee. We write position statement for IEEE. And also I'm the chair of the Cyber Security. So I just wrote a Cyber Security position statement and it's approved by IEEE USI. But I see there are some holes in the things which we wrote because we only address on the IT side, not on the control system side. And that's a huge, big holes. So I would like to talk to you more, like maybe we should have some kind of position statement related to the control system and we can make some recommendations. And after that, we can send to, I have good friends in the Senate and Congress, like I know a lot of them. And so we can send it to them and have them vote on. And I also know Biden's too. When he come to Seattle, so I had to meet with him several times. So we can send to White House if you have some good ideas. So the point is, I think I should talk to you more and maybe you'll have phone numbers provided to us, then I can call you. And
Yes.
then because the one you have it's a big wealth of knowledge, which is really needed in our country. So we need to talk more and put those things into practice. So make our country to be more safer.
Well, this would be great. Mike, thank you for reaching out because this connection could be very, very, very important.
Okay, yeah, Sherry's the top in the Seattle area, so she's always putting on presentations. So I want to wrap it up. So we'll share Joe's contact and Sherry's contact information with the rest of the group. So once again, this is the IEEE Consultant Network Tech Talk for December, and I want to thank everybody for joining us today and have a good day.
Thank you.
Bye-bye.
Thank you very much for organizing this. Thank you very much.